I never even thought about it like that.
Oh, quick question.
Yes.
When are we in the quiz grades back?
That will be Monday. We're going to do it right before doing a lab.
Okay, cool.
Okay, so the next couple of days are planned out. Today we're doing this review. Monday or Tuesday, whichever day we have, we're going over that group quiz and doing a lab on rolling things. Wednesday there'll be a practice test, and then Thursday a test on the rotation stuff. Okay? So today we're going to do a review, going through all the types of problems you might see. The only thing that's not on this handout is conservation of angular momentum stuff, because it's a lot to do in one day. But it's your responsibility to kind of figure out what things are making sense, what things are not, and then to review what you need to review. But you do have a week to do it, so there's a lot of time, but it's not going to happen on its own. This is basically all the formulas or kind of relationships we've talked about over the past 2 weeks. There's the linear version that's like the first half of the year, and then the rotational version. Before we start on this, are there any questions about any of the symbols and what they are or what they mean? No?
Oh, seeing it laid out in the chart like this makes it make so much more sense.
No questions? All right, just some things to fill in the blank. What is torque equal to? There's a couple of different ways to think about it.
R
Could be r of sine theta. It could be the perpendicular distance times f. That's often the case where there's not an angle involved. Then it's really just r times f. Moment of inertia for a solid disk about its center. You don't have to memorize these, but maybe you're starting to. 1/2 mr squared. But all these things, all these shapes have the same pattern. It's just what is that thing in front will change based on the shape. For rolling without slipping, how fast does a ball roll?
Omega.
Perfect, omega r. If you have something in static equilibrium, what things are true? What is true about the sum of the torques? 0. What else has to be true? What? And it could be moving. Equilibrium means not accelerating. This means no angular acceleration, but something could be not spinning but still accelerating. So what else do we need?
acceleration
Acceleration is 0, and when would acceleration be 0?
plus forces.
Perfect. Sum of the forces equals 0. Angular momentum is conserved when what? Sum of the torques is 0. In a ramp race, what shapes are going to win?
The sphere.
So if we have sphere, sliding block, and a hoop, and a disc, those are the common shapes. Which one will be fastest?
The sliding block.
The block?
Because the most energy goes into translational.
Yeah, because 100% of the energy goes into translational. First page okay?
Yeah.
All right. We're going to go through some tough problems here. The first one is the easiest. Okay. So this first one is very straightforward. You're just plugging. A solid disc has a string wrapped around it. A constant force of 50 newtons pulls on the string. The first part is find the moment of inertia. We have the formula here, so if we have the mass and the radius of the disc, we just plug that in a calculator and we'll get a moment of inertia. Do we know all the things about it? Yeah, 1/2 times the mass reduced to the kilogram. starting from rest, what is the angular velocity after 4 seconds?
It's just 50 radians per second times 4 seconds.
Yep. So we use one of the kinematic formulas. These are given to you. The final angular velocity is the initial angular velocity plus alpha t. But the initial angular velocity is 0. So this is final angular velocity is the acceleration. That's 50 radians per second. Per second squared times 5 seconds or times 4 seconds. So omega f is 200 radians per second. Then finally there's part E. The rotational kinetic energy, how do we find that? That's 4, 50 times 4.
Alright, wait, so
Oh, I see right there.
KE rotational is 1/2 I omega squared. So that's 1/2 times 0.06 times 200 squared. It's 1,200 joules. Questions on this problem? No?
This is the easiest one?
Yeah.
Serious?
Yeah. If you want to have ChatGPT explain it, that is a great resource. Okay. Statics. Statics means we have some object that's not accelerating, either linear acceleration or angular acceleration. So the key idea here is that the sum of the torques will be 0. About any point, we get to pick the point, and the sum of the forces will be 0. That's the sum of the forces in the x and the sum of the forces in the y direction will all be 0. And we have to kind of work with all three of those ideas to fully answer this question. So we've got a beam. I'm going to sketch this. There's some hinge, and there's a beam like a pole sticking out 4 meters. And there is a tension cable helping hold that up. And there is a mass hanging on this beam at 3 meters. How do we describe the weight of the beam itself?
Is there the mass of the beam plus the mass of the weight that's on the beam?
So we've got the mass here, and what's the weight there going to be? It's 10 kilograms. Gravity is about 10. It's about 100 newtons, right? But if we want to describe the weight of the beam itself, where do we put that? Perfect, right in the middle. And how much does the beam weigh? So that's its mass. What's its weight then? 200 newtons. And then what direction is the tension in here? Up and to the left, it's in the cable. So there's some tension there. And then there's some force here from the hinge. What direction will that force from the hinge be? So it depends on where the tension cable is attached. So think if you're pulling from here, and this force is down here, it's not going to want to go down or want to go up. Probably not sure.
it seems like it should have just a rail to go down.
What's the answer, Mr. Redler?
So you could imagine with like a, if I'm holding this up a little bit, like I'm the tension. Right now this wants to go down. It's pushing down on me. If I was holding it here, then it would want to go up. Imagine this is the tension cable in my hand. So if we're holding it way far away, usually this wants to go down, which means the wall has to be pushing up. Does the clockwise, rotate clockwise. These ones, this 300 here, right? But for torques, we've got to multiply by how far away they are. So we've got minus 200 newtons. And where is that negative 200 newtons located?
2 meters.
2 meters. It's at the halfway point. Then we're adding another negative 100 newtons. Where is the weight of the...
3 meters.
At 3 meters.
That's all it matters.
And then we're adding, because the tension cable is trying to make it go counterclockwise, which is the positive direction for rotation. And we're using the torque formula, which is F, which in this case is the tension, times R, which in this case is 4 meters, times sine of the angle. Do we know the angle? 50. Can we simplify this at all? And first, what do we know this all adds up to?
0.
0. So now we're solving for t, and we'll get a number. So we've got negative 200 times 2, that's negative 400, minus 100 times 3. So in total, this is going to be negative 700 newtons. So this will become 700 newtons equals t times 4 times sine of 50. I combined them and then also moved it to the other side. How do we now solve for t?
By 4 sine.
Yeah, so the tension will be 700 over 4 times sine of 50. $700 divided by 4 sine 50 is 228 approximately. So I'm going to mark that here, 228 newtons. So we've done part A, which is by far like the biggest part. What can we do now? We can find the hinge forces. So how do we start doing that? Yeah, I know that all the vertical forces have to add up to 0. So can I find the vertical force from the tension? Yeah, so I can imagine this tension. I want to find the vertical and horizontal components of the tension. So I can imagine the tension here as like a triangle. And I know this angle here is 50 degrees. So if I know the hypotenuse is 228 newtons, I know that's 50 degrees. What's that side going to be? This is trigonometry, yeah? You're supposed to know this. Do we use sine or cosine to get the opposite side? So sine of 50 degrees equals the opposite side, which will be the vertical component of the hinge, divided by the hypotenuse, 228 newtons. So the vertical component, if we solve for the horizontal component of the vertical component of the hinge, we'll get 228 minus that 50. This is about Okay, that was a very long problem.
You probably shouldn't put something like that on the test.
Hmm?
You probably shouldn't put something like that on the test.
Maybe part of it.
Yeah,
Maybe just the
the
tension
first
cable,
part.
just the first part probably.
We do a test on the addition.
It's just the same skill.
Questions or okay to move on? I am going to post the video of going over this if that's helpful later. Okay. In the interest of time, for rolling, I really recommend you use this formula or memorize this. This will also be something we are doing on the lab. That the final velocity of something rolling down a ramp will be root 2gh over 1 plus c, where c is the coefficient in front of the moments of inertia. So whichever of these has a bigger number is going to go slower. So which will be faster? The sphere. Sphere is faster. To actually calculate those velocities, so the final velocity for the sphere will be root 2 times g, we'll say that's 10, times 2.5 over 1 plus c, which will be 1.4. The final velocity for the cylinder will be square root 2gh over 1 plus c, which will be 1.5.
Wait, Miss Mara, why is the C 4?
Hmm?
Why is it 1 times 4? And the,
1.4. So this is 5.97 meters per second. And the cylinder, $5.77. Is that okay? Okay to move on? All right, I think these are the hardest problems. So we're going to just go through it. We've got two masses hanging from a pulley. We could draw a free body diagram for all three of the objects here. If we're doing a linear system for the free body diagram, we draw the mass M1, and then we label all the forces acting on it, and we draw the mass of this shot. What are the forces acting on M1? F2 down, and then normal force going up. Perfect. And then it's the string force. What should we call the string? Perfect. T1. Now, for doing a free body diagram for a rotating object, we draw the shape because the shape is important. And what are the two forces acting on the two forces acting on the pulley? There's T1 and T2. Are they going to be the same? No. Which one's going to be bigger?
T2.
T2, because it's going to be accelerating this way.
they all say no?
Why can we ignore the force from where it's attached to the table?
That's not like part of the string. Like it's just sitting.
Because it's at the radio. It's at the center.
We're going to assume it's at the pivot point. So when we do the try to find the torque, it's going to not matter. And then for M2, what are the forces acting on that?
String, gravity.
There's the force of gravity down, and then there's T2 going up. Which one's going to be bigger?
T2.
Is it accelerating down or up?
Did it say that? Maybe.
This is a frictionless table, and it starts at rest. So M2 is probably going down.
So that means the gravity's
That means FG is going to be stronger than T2. We're going to write Newton's second law for all the linear parts. But the key idea here is all the accelerations will be the same. We're going to call this direction of positive motion. That's the positive direction. So for M1, acceleration is the sum of the forces over the mass. What are all the forces accelerating M1? Just T1 for M1. Here we're just talking about the M1. Acceleration is T1 over M1. And for M2, acceleration is the sum of the forces. What are the forces? Which one's positive, which one's negative? We're considering the whole direction of motion positive. And what's the total mass of M2? And then for the accelerating disk, the angular acceleration is the sum of the torques. What are the torques acting on the fluid? There's two of them. T2 minus T1, all times R, because we have to multiply forces times the radius for torque. And then what is the moment of inertia of the force? 1/2 m r squared. Now we could also express this in terms of A instead of alpha. Using the bridge equation, A is alpha over R. We could solve that for alpha. Alpha equals, A is alpha times R. Guys, please keep quiet.
Wait, so we just put that whole thing over the radius?
Huh? We want to write everything in terms of A, not alpha, because we've got linear stuff and rotating stuff. We want to make it all linear to solve for A. So if A is alpha times R, and we solve that for alpha, we get alpha is A over R.
Why is alpha over
Hmm?
Why is alpha over
In which part?
on the left side?
On the left side? That comes from Newton's second law. Alpha is the sum of the torques over the moment of inertia. You guys stop giggling, please. So then we could rewrite this equation as A over R equals T2 minus T1 times R over 1/2 mr squared.
Or not alpha? Oh, wait, never mind.
Now it's A because we...
Never mind.
Wait,
Now the really long way to do this is then we could solve this for T2, that for T1, substitute them in here, and then solve this big equation. But there's an easier way, which I recommend you use. No. So the acceleration is the sum of all the forces over the sum of the masses. But if we treat this as just one big system, we can just describe all the forces. What are all the forces acting on the whole system? Ignoring the tensions, any internal forces.
gravity is a force?
There's only one force accelerating the system. What is that? Gravity of on which object? M2. And then we can just add up all the masses of everything. And there's three masses. What are the three masses? M1 plus M2. And then we can use the effective mass of the pulley if we want to. Does anyone remember how we do that? That is 6 kilograms times. What are all the masses combined if we use half the mass of the pulley? 4 plus 6 is 10 plus 1 over 11. So 60 over 11. 5.7. Now, what we did here, we kind of just skipped to it. Because solving the three equations is hard. I think doing that's a lot easier. So that's what I recommend doing. But going through the force diagrams is helpful because you can see what's acting on each force. So once we have the acceleration, could we then plug accelerations into here to find tensions if we had to? Yeah, we could. Do you want to do that now? Sure. Let's find one of the tensions just for fun. Which tension should we try to find? So if we want to find T2, we now know that the acceleration is 5.5, so we could say 5.5 equals, do we know the force of gravity on M2? That is,
60?
yeah, 60. Minus T2 over M2, which is 6. Could I solve this for T2 now?
Yeah.
Yeah, multiply both sides by 6. So 5.5 times 6. And then subtract 60 from both sides. So you get 27 newtons. Okay. If it's accelerating and the string is cut, what's going to happen? Does the pulley keep spinning or does it stop spinning?
It'll keep spinning.
Yeah.
What's the, unit for the 27?
That's newtons. All right, so these are all the topics. All these things you could look up if you want to ask ChatGPT. All these topics you could ask ChatGPT for help with. If you want on Khan Academy, these are all named like what they are. On the Fab Physics site, these are Unit 5, these are Unit 6. Some common mistakes. Student claims the tension on both sides of a massive pulley are equal. Why must that not be true?
They're equal within equilibrium.
Yeah, it wouldn't accelerate. And last one, a student says a hoop beats a disc down a ramp because it has more rotational inertia, so more rotational kinetic energy. What is the problem with that statement? Is the thing in quotes true or false? Other thoughts?
False.
Why is it false?
Because it makes more sense.
So what is rotational kinetic energy?
It's like the amount of energy that's being.
It's 1/2 I omega squared. So if I gets bigger, does rotational kinetic energy also get bigger? Yes. But there's only so much energy to go around. So if you have more rotational kinetic energy, what do you have less of?
Transitional?
Perfect. you have more rotational kinetic energy, then you have less translational kinetic energy.